I believe this is the last long-form talk of the program, which is, you know, spectacular. He doesn't have a microphone yet, so we're going to talk about the Cubs for a minute. Let's see. So who's excited about open spaces this afternoon still?
Oh, yeah.
All right. Who's a little, like, tired from watching a Cubs game a little late last night? All right. I'm like really, really tired and still running on full positivity. So it's a weird mix. Let's see here. Did everybody get a scarf?
Right.
Everybody got one? Okay. If you didn't get a scarf, go see the registration table and you can get one. Because we have a few left and we really shouldn't based on the math that I can actually do in my head. So if you didn't get one, please do. Or are you mic'd up yet? No, you're still not mic'd up. Go Cubs. I don't really have any other announcements. There's a meetup that happens once a month. You should be here if you're in the Madison local area. You can follow us on Twitter. If you want Slack access to the Madison DevOps people, you can talk to Josh and Christian. And now we're actually going to have the last long-form talk of the program, which is awesome because we're going to hear about chaos engineering, and it's an Optimist guide. So I want to say you're a Cubs fan because it says Optimist guide, but I know you're actually not a Cubs fan. It's okay to be wrong sometimes.
Yeah, I was going to say it was fun. It was fun watching all of the people that were super excited last night. But at the same time, it was fun to watch everybody having such a great time because it's pretty interesting. So first question, who knows what chaos engineering is, or at least has like a general idea what the concept is? All right, that's about half the room. All right, cool. So the concept is, hi, I'm Andy, and I'm an optimist. This is part of who I am. I naturally believe that I can solve a problem, and I go attack that problem thinking that I'm going to solve it in some fashion, whatever that ends up being. But being an optimist can be incredibly hard when like everything is just broken all the time, which is like basically how software works. So a little bit about me. So I'm a senior software engineer at Sports Engine. I've been a Ruby developer for 9 years. Did this operations thing for like 4 years now. So I'm on the platform operations team at Sports Engine. And then like the other thing about me is like I'm super into complexity, like as a thing, and then also safety that sort of like falls in a similar line of systems thinking and all of that. So awesome podcast, Pre-Accident Investigations podcast by Todd Conklin, if you're interested in or wanting to get to know about safety. Also, Sidney Decker is like kind of a genius. So the field guide to understanding human error is all about plane crashes, but like sort of understanding like how the events unfolded and figuring out how to do that correctly. So I'm also a Packers fan, which like I'm kind of surprised like has not come up yet. I'm from Minneapolis, so like I kind of have to pump that since I'm in Wisconsin right now. So. Other thing about me is like I'm like a member of the Allspa fan club. The cards are actually just PDFs. Yeah, so I'm not necessarily like there's not an official club, but all you have to do is like have a PDF and then you can be part of the Allspa fan club. Okay, so Sports Engine, we were acquired by NBC Sports in July. But so we were a startup. I started working for them back in 2011, so I've been there for 5 years. And we do, we're a sports technology company that focuses on youth and amateur sports. So we provide websites, tournament management, registration for like little leagues, and then like amateur sports of any kind. So pretty interesting field that I'm in. I enjoy about the work that I do. We have 10,000 different domains that we manage for our CMS, so like fucking DNS, but other than that, it's like pretty great. So the concept of our platform, we like to call it sort of this solar system architecture, where we have a monolith because it started as a single Rails app that was the entirety of our product, was just this one Rails app. And then as we grew and added more products, we started building out services and like doing the whole microservice thing. And we've been breaking pieces out of it, but just for some context, like the design of our system, is there's one thing in the center of the our universe that's like the most important thing, right? So just to give you an example of like the work that I do, Ruby's timeout library doesn't like actually work. I found that out the hard way whenever I was trying to like fix something, and it's like just never coming back, even though like I would change the timeout to whatever I wanted it to be, and it just never worked. There's a great blog post about why that is, so if you want to check out Mike Perm's blog post on why Ruby's timeout library doesn't work, that's a thing. Also, we have this node framework that we built ourselves. Not a great decision, do not recommend doing that. Turns out there was like this vulnerability in it that if you make a request to it, it basically kills the process because it didn't properly capture the exception because the actual URL was invalid. So like we found that using our like Nessus security scanner. It was like sending stuff. We're like, why does this app go down? And we send and their view from it is like, we helped you find a DOS endpoint, and like they're pretty excited about that. And then the other thing is, so there's a bunch of different Ruby app servers. Well, there's one we use in particular that we had this app that was sort of a legacy app that we inherited. So we got acquired. We also acquired 5 companies in the last 6 months. Also like a super hard problem. And trying to figure out like how to like get people into the fold is pretty interesting. But as part of that, we got this app that was sort of unfamiliar to us. And all of a sudden, like we were trying to get it onto our normal tech stack using our normal like application server. And all of a sudden, like we turned it on, and then it just suddenly was just like stuck and wouldn't do anything. The app server itself would no longer process more requests, and we're just like, what is going on? It turns out a stream got closed, and then like that broke the app server, and it just was no longer working anymore. So like just weird, bizarre problems that like I actually found like so much joy out of working on these problems. That probably says something about me more than anything else. But you know, I learned a ton about how the actual applications work. I have a background in software development. My title is actually software engineer, but these are really operational problems. But then you also need the context of like what the app is doing in order to be effective about it. And it was great just tracking down these problems. My coworkers were just like, we're like all huddled together, and we're just like, because it's like an important problem that we need to solve, and it's like the first thing that we need to get done right now. But like real talk, I enjoy breaking things. It's actually something I like a lot. It's kind of fun to just watch a system just fall down and die. So like that's me. That's a picture of me. So the concept is systems thinking can be counterintuitive. So I'm into systems thinking. It's basically, Dakota was talking about it a little bit in his talk earlier, that we're looking at the system as a whole and not its component parts. But it can be counterintuitive because the choices that you make over here can come out of the system over here in ways that you wouldn't expect. And like, if you look at the system as a whole, that's how you can determine whether the choice you made over here ends up with the outcome that you want. But the way you actually attack like a problem from a systems thinking point of view is like through feedback loops, right? So there's emergent properties that come out of the system as you change things, that then you use that emergent property to make more choices, to make more changes, and to keep moving forward. And success and failure is like pretty hard to define. The system is large, it's very complex, and the outcome is not necessarily good, and it's not necessarily bad. But complex systems are pretty good. Like I like them a lot. There's just like this weird, there's just weird hard problems that exist only in complex systems. So 3 truths about complex systems is that they're inherently unsafe. So a system that is running and is like that exists is just filled with latent problems, right? So there's 3 bugs I described. All of those applications worked. They were fine, and then all of a sudden, like these bugs showed up and were like huge problems. And failure is just a normal state of the system. It's just sitting in the system as part of it. And failure, so the last key part of this is that failure can actually make your system stronger, which is where this comes in. So, big reveal. Chaos engineering is the discipline of experimenting on distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. So this comes from the principles of chaos engineering. So Netflix, sort of the people that named chaos engineering, it was already a thing. So failure injection is a thing that's been around for quite a while. But Netflix is like they're really the sort of leaders in this space, right? We'll get to that in a second. But distributed systems are complex systems we touch all of the time, right? Like if you operate an application with more than one server, it's a distributed system. Like that's all it takes. So basic principles: build a hypothesis around steady state behavior, vary real world events, and then learn from the changes from the system's steady state. So this is how you perform an actual chaos experiment, is by first you have to understand like how the system functions, like what are the outputs of that system, and it's sort of like standard operating procedures. And then start to change variables, and we'll talk about what those variables are, and then like learn from that, right? So like you have to take direct action after you do that, or it's just a waste of time. So build a hypothesis around a steady state behavior. Really what you're trying to do is attempt to understand like how the system functions. In a distributed system, the network is the backbone of that system. Everything about how it works flows through the network. So it's one of the key pieces that not a lot of people think about whenever they're trying to resolve problems, because like it mostly works, right? TCP is a great protocol. It retries, like it's very reliable by itself. There's not much you have to do. But the other thing is like start figuring out how to measure the outcomes, right? So application performance monitoring is a thing. It's super useful. New Relic's here, go talk to them if you don't know what that is. So you're just trying to figure out like how your system runs and get to know it better. So once you've sort of defined the baseline, you can then start to figure out variables that you wanna change. And there's a lot of ways to do that. Two that are like pretty popular are one, like just turning servers off. So Chaos Monkey, that's what it does. And then two is like adjust the network. So the scariest thing in distributed systems is slow network. Because if a server turns off, you're gonna get a reply back and it's gonna be fast. And it's not really a problem, but if it's slow, you're now then like waiting all this time and then still not getting what you want, right? So rule number one, never trust the network. And systems are pretty, they resist fail. So systems that resist failure, that are like highly reliable, tend to fail catastrophically. They don't just sort of drift into like this weird state of failure, they tend to just fall down and die. Because they're super reliable and it takes a big event in order to make it fail catastrophically. So, learn from the changes to the steady state, right? So the last thing you have to do is actually learn about what happened. So you change something, you just started turning some servers off and you've seen how the system reacts when you do that. The last thing you have to do is decide what you want to do because of what you learned. And just figure out, like sometimes it's super obvious. If you slow down the network and it takes down, so say you have 10 services in your platform, you slow down the network to one of them and it takes down 8 of them, like you clearly have a problem with like how these services communicate and you're not protecting yourself enough. So like the obvious thing to do is to improve that. Next big thing that's super important, at this point, what I'm describing, you can do all of these things in staging environments. I highly recommend you do that. If you've never done this before, do not do this, because that will end badly, right? So, but the key to chaos engineering being effective is that it runs in production. So it's actually making your system stronger because it's just running all of the time. Highly recommend doing it when you're like actually working, but not on the weekends. But that's the concept, is that you're actually actively doing it in production, right? Yeah, little notes. Okay. This is just this dumpster for the record. So So why would you run it in production? It's because it's impossible to create a duplicate system that matches exactly what production is. There's always going to be variables that are going to change how the system is affected by your experiment that like would not happen would happen differently in staging than production, right? And a failure in a production-like environment is not going to be quite the same. You're not going to have the same exact traffic type. You're not going to have the same exact, even if you have the same exact server type, it's just not all of it. There are so many variables in a complex system that you cannot recreate one. Like, there's a complex system that exists over here, and there is no way to make another identical complex system. Do not run a chaos experiment that you've never tested, right? Key point, if you're gonna run it in production, you have to have tested how that works and like have a general idea of what's going to happen. Because you could just take the entire platform down like inadvertently, which is fine, you're gonna learn a ton from it. And that could happen anyway, but do not do that without actually without attempting to do it in your staging environment to at least have a better idea. And fake it till you make it, right? So you can do it in staging. If you cannot sell this as a concept to do in production, which believe me, that's incredibly hard to do. People are very afraid of that type of thing. You can totally fake it in a production-like environment, and it's going to give you a lot of information. Like I said, it's not exactly the same, and that's why like the folks at Netflix believe very strongly that you have to do these experiments in production. But you still can fake it till you make it. In fact, that's mostly how we do our experiments. We don't run very many experiments like actively against our production platform. So, cool. What's next? So, like I said, network latency is a distributed systems kryptonite. Increased latency just makes the system crumble and fall down. So there are a bunch of tools that'll help you do this. Toxicroxy from Shopify, Comcast, ironically, that's the one I use, work for NBC, kind of awesome. And then Chaos Monkey. So Netflix just recently released Chaos Monkey 2.0, and it's just a Go binary that you need to run Spinnaker. So like, we can talk about Netflix tools at some point, but there's like a lot of things you have to do in order to use some of their tools. So I'm a big fan of like finding something simple and just trying it out. We learned so much by just poking around with Comcast, which is just a wrapper around, it's like TC and IP tables, right? Like it's the simplest solution to a problem that then like told us so much about our system. Right, exactly, this is my point. Distributed systems need to talk to each other. That's how they work. And if you slow that down, you're gonna find interesting results, which is why I recommend that as like the basic starting point. Right, more of that. So, next thing you should do, after you do this and you see it fails miserably, Google that and then you'll find the way to solve the problem. So circuit breaker pattern is the best. Big fan. It is the way you prevent slow network latency from totally destroying your platform. Netflix has your back on this too. There's Hastrix, so if you're on the Java stack, Hastrix is a super awesome tool that's like really robust. That is a great implementation of this pattern. But like, why would you even do this? What you're looking for is these latent failures, right? So there's just the problem with complex systems is that they're just inherently unsafe. And so what you're trying to do is you're surfacing those vulnerabilities, those bugs, those are just failures waiting to happen. You're trying to bring them to the forefront. And it's really easy to assume the system is safe because it's just running all the time, right? Like it's just running, it's working. I mean, you can have 4 nines of uptime, but like have a catastrophic failure. Like it's not that far away. You're really close to it. But you just don't know it because you're not actively looking for the weird ways that can happen. And it's impossible to find all of them. There will be more of them. But you can at least attempt and make progress. So the prime directive of chaos engineering is to learn. Like the goal is learning. By learning, our system can continue to improve and grow, right? Like we've built these reliable systems. So what's next? What's next is we make our systems resilient. So the key to resilience is adding capacity to fail into your system. So a circuit breaker gives you the ability to have slow network and not affect this cascading failure of TCP retries, right? Like that gives you the ability to withstand that storm until it goes away. You're gonna lose functionality, but we have to stop thinking about like our products being all the way up or all the way down, because in order to be resilient, you can't be all of those things all the time. And like we have complex systems, and that's the state, regardless of like whether you want it to be or not. That's actually how it works. So adding capacity to fail is the key to creating not just reliable systems, but resilient ones, right? So now for something completely different. Organizations are distributed systems. I loved Dakota's talk before this because he was like setting me up. I thought that was great. So he was talking about humans as complex systems, basically, and I'm talking about groups of humans as complex systems. Right. So like I'm into this too. Wait, what? So how do we apply chaos engineering to other social technical systems, right? So like organizations. That's not a thing. But Conway's law actually says that it kind of is, right? So Conway's law is an organization which designs systems are constrained to produce designs which are copies of the communication structures of these organizations. So that's Conway's law. What that actually means is you're basically stuck. The only systems you can create are ones that map how you function as an organization and how you communicate as an organization. So if you want resilient systems, you actually kind of need a resilient organization. So resilient teams create resilient systems, right? Teams are kind of like services. You've got a bunch of them, they interact with each other. There's sort of a communication thing going on that is the network, right? And so communication is sort of the key. And like you're trying to figure out how to make that communication structure more resilient and create new, you want to add capacity to fail into an organization. So failure injection is kind of one of the ways to do that. You're learning where the communication paths are within your organization. So what does failure actually mean here? This is a bit of a stretch. I'm probably conflating things that maybe aren't true. And I acknowledge that fact. But it also, I think, because of Conway's law, like I feel like this has to be true. Because Conway's law is a law, it's not a theory. So how do you make failure a thing? Is you shuffle people around. They are like, if you're on a team and you're bonded on a team, there's sort of like a sense of ownership around your like team structure and highly collaborative environment. You talk to them every day. So move people around and it's going to shake things up. It'll be kind of interesting. Your team leads will not like it at all because they want to know who's on their team, and if you're kind of moving them around, it'll be weird. But highly collaborative teams can fall apart when there's a communication breakdown. So example being like there's this new service that somebody's working on over here, but like nobody told the operations team that they got to spin that service up, right? So like, how do we learn about these things before like, oh yeah, product's gonna launch this thing like in 2 days, and like nobody told us that it's like ready to go, right? So how do we prevent those kinds of things from happening? And we just create pathways that like don't exist. I mean, they exist, but they're not formalized enough to be more like sort of a walking path through a courtyard, right? There's the sidewalk, and then there's these actual dirt paths that have been generated by people walking through it, right? So create more pathways for communication. This adds more avenues of communication, making failure less impactful. So like, what happens is, so the concept that I'm talking about is we have this thing we call operations reps, which is actually one developer from like every team in our organization. Then we classify them as an ops rep. And what happens is they'll do a rotation. There's like 4 of them. They'll do a rotation once every 4 weeks or every 8 weeks, because we do 2-week sprints. So they spend a sprint on our team and like actually do the work that we do. And they get to know like how operations happens, and we're completely capable of teaching them how we actually function as a unit. And then they start to take that information back, like you know, solving performance problems that maybe they didn't know how to do before. Or like writing shell code, like getting that to be a thing. It's like you got a config file change. Why do we need to make a config file change for you? You just make it yourself. So that concept, we're just like sort of moving some of the work off of our team, but then also making it so that when that meeting that developer is in realizes that we don't know about the thing yet, right? They can be like, hey, that thing's gonna happen, so like you need to get your shit together because like it's gonna fall apart if you don't. And that allows us to have more communication that maybe somebody just forgot about. But like if you add more pathways, the chance of that completely falling down starts to go down. So how else can we break our organizations? This is sort of my final question. I'm not really sure I have an answer to this yet, but like I'm definitely thinking about it. It's because it has to be, there's got to be more variables. I'm just not really sure what they are yet. So if anybody has thoughts about that, we should talk about it. But yeah, stay awesome, and thanks.
Anybody have any questions? We do have a couple minutes.
Great talk, Andy. For orgs that think, well, we want to experiment with chaos in that we want to know we'll be resilient to failure, but what about things like data corruption? How can we safely introduce unpredictable elements into our production environment, and how do we make that case to people who are going to say, but what about things going wrong that we can't reverse? Can you talk a little bit about that?
Yeah, I mean, that's a good question. It's not easy. It's not. I don't think it's a solved problem. Like Netflix isn't screwing with their data when they're doing chaos engineering. That's not something that they touch at all, as far as I know. I mean, they have like a half a dozen different this part of the simian army, as they call it. The like key ones that they do is they turn servers off. They turn availability zones in Amazon off, and then they also have a thing that they call a chaos Kong, although they're turn off an entire data center, so an entire region in AWS, and then like all of the traffic will automatically move. They have this tool that's called Visceral. That's pretty sweet. If you're interested in seeing their other thing that they named is intuition engineering, and there's like this graph of like data movement between data centers. It's pretty cool. But as far as like, yeah, I do not recommend like touching your data layer at all for this. You could do that as long as you didn't do it in production, maybe. So like you could learn a lot about like what your database is, how your database is going to react by testing one that's the same size and then like attempting the same problem. Because it's good to know, right? Like Kyle Kingsbury's done a lot of work on that. Read everything he wrote about that because there's lots of good information if that's something you're curious about. But.
Cool. Awesome talk. Thank you. So you talked about Conway's Law and the kind of parallels between systems, and we're talking about like systems failure. Have you thought about like how you could break your actual teams and see if like the sort of non-technical part is resilient?
Well, so we sort of did. I think is how I would describe it, because the teams are continuing to function. There's some like grumpy managers a little bit, which I think is maybe the pointing that it actually kind of did. But it's working. We're like getting things now that we didn't have before. They're like it's like what the coolest thing is like they're like active contributors. They're like bringing new ideas in, and like we're getting like these benefits that we did not anticipate at all, that are coming in as a result of what we did. And it's like, I mean, it's kind of new. We've only been doing it for 3 months. So we're still like kind of trying to figure it out. One of the key things is we want to learn from what we're doing and make sure we're doing the right things. So we like hold retrospectives at the end of the sprint with the rep and try and figure out if there's things we can change, improve. Maybe is this something we should be doing at all? Because we're having that conversation so that we all kind of agree that we're doing the right thing. And by coming to that consensus, we're like making our organization resilient because we all have the right context and understand what we're trying to do. Yeah.
All right, thank you so much.